Hello, am I audible?
Yes, sir. Yes. Now it's on.
Okay. Okay. Yeah. Okay. Okay. I'm sorry. I think yeah. was- So I was talking about detecting changes in Sentinel-1 imagery. We are doing this part 4. We have basically done e.authenticate and e.initialize, and then we will see this new library with some functionalities, interactive functionalities. It is called EESAR uh, sequence. So you run the application from eesar.application, and you can see that this kind of an interactive view opens. So this interface we'll see how to use. So the sequential SAR change detection method that we developed in the first three parts of this tutorial is pixel oriented. That is to say, it is based entirely on the statistical properties of each and every multi-look pixel in the observed image series. For this reason, it is best to limit your analysis to a region less than a few thousand square kilometers while interactively visualizing and exploring results using this notebook. Furthermore, since we are analyzing time series for changes, the reflectance images involved must completely overlap the region of interest and have been irradiated from the same position in space. This means choosing either ascending or descending node and only one relative orbit number for any given sequence. Now we'll walk through this. So to get started, let's see how to generate a small change map. In the widget interface above, choose platform A. So you can see we can choose whether we want platform A or platform B. So these are the different options from the data. Leaving all other settings as it is. Select a small area of interest near the town of Zulich with a rectangular or polygon draw tool. This will enable the collect button. So you have to select a small region here around the town of Zulich. So for selecting, you can just do this, and this selects your region. This will enable the collect button. So where are we having the collect button? Let's see. Click it to collect an image series, the details of which are printed in the info box at the bottom. So where is the collect? Yeah, here we have the collect button. Okay. So click on click it to collect an image series, the details of which are okay. Yeah, this is printing this detail running on the archive. Copernicus S1 GRD, images found 36, platform A, number of 10-meter pixels contained, acquisition dates, relative orbit number, mean misses. Okay, so this is okay. Also visualizing this synthetic aperture radar data. The raster overlay shows the complete swath of the last image in the sequence. While the overlay is fully rendered, the preview button is enabled. So you can see that we have this preview button is enabled. The preview button will now trigger the change detection algorithm at the scale selected by current zoom setting. The color coded change map is displayed. So we will click this preview button. Okay, so this is running, and okay. So the color coded change map is displayed, showing for each pixel the interval within the series of first detected change. So palette is black, blue, cyan, yellow, red. The map displayed is set by radio button next to preview. So the radio button next to preview sets the map. So you can see here, this is the change map that is being shown in this plot. Since processing is carried out in parallel, the change map is built up tile by tile. As explained in part 3 of this tutorial, the zoom setting can falsify the result somewhat depending on the pyramid level at which the calculation is carried out. Nevertheless, it is often convenient for generating a quick overview. You can see the effect by zooming in and out. Deselect the quick preview checkbox to override it. Now the calculation is carried out at the full 10 meter pixel scale, irrespective of the zoom level chosen. So we have to deselect the quick preview checkbox. Where is the quick preview? Yeah, so you deselect the quick preview checkbox. Now, if we do this, okay. So now the calculation is carried out irrespective of the zoom level, but can take considerably longer. So this is the algorithm is doing change detection. It is calculating whether change has happened or not. If and when you are satisfied with the previewed result, you can export the change maps to your Google Earth Engine cloud assets with export to assets button. So export to assets button is here. What this will do, you can basically export the assets or the image to your Google Drive, or you can export to Drive, or you can do an export to assets. So we'll see the widgets. We have platform. So choose one or both of the Sentinel-1 satellites. We have the platform here. We have pass. Just choose ascending or descending mode. Rel orbit, which is the relative orbit number, is set to 0. All orbits are included with images which overlap with the area of interest. Start date, which is beginning of the collected time series. End date, which is end of the collected time series. Collect, start collection enabled when area of interest has been chosen. Upon completion of this last Sentinel-1 image in the sequence is displayed. And then we have the significance level for the likelihood ratio test. We have the median filter, which is run a 5 cross 5 median filter over the change map before displaying or exporting. So we will see we have rel orbit, start date, end date, collect, stride. Where is the, yeah, we have the median filter. So this median filter will basically just take the median of a 5 cross 5 box. Then we have stride. So select only a subset of the collected sequence. For example, the value 3 will collect every third image in the sequence. And we have show S2, which is display the most cloud-free Sentinel-2 image found within the chosen time period instead of the last Sentinel-1 image. Then we have export to assets. So it creates and runs a batch task to export a change map as a raster to an Earth Engine asset. So for a time series of K images, the exported change map consists of K+2 bands. So then we have export to Drive, which will export to the Google Drive in a GeoTIFF format. And we have preview, which runs the change detection algorithm and preview results according to the chosen settings. Review asset displays a currently selected change map asset according to the chosen settings. Plot asset plots the proportion of change pixels in the B-map bands of the selected assets as a function of time. Then we have bitemporal. So it's an option in the preview whether we want bitemporal change map or something else. And then you have interval. So choose the interval for the bitemporal map. The first, which is preview the SMAP band, and last is preview this CMAP band. Okay, so you can set the opacity. Opacity is basically if you set it as, where do we have the opacity here? Okay, so this plot you can see this has got opacity is 1. If you set it like 0.8 or 0.9, you will also have the background map visible. So it will be slightly transparent if you by setting the opacity. Okay, so then some examples. So one is the surveillance. So remote sensing, surveillance or monitoring applications are most often associated with very high resolution satellite or aerial sensors. The Sentinel-1 C-band group range detected imagery on Google Earth Engine is obviously much less applicable to such tasks. This is mainly due to the relatively poor spatial resolution. So 20-meter is actually, they are saying, is a poor spatial resolution for surveillance, and the ever-present speckle in the archived images. On the other hand, a guaranteed all-weather revisit time of 6 days might be usefully exploited in some circumstances. So one of that circumstances, so seaport activity monitoring is one such possibility. With the frequency of large vessels arrival and departure, usually quoted as ATT or average turnaround time, being in general of the order of days. Thus, a change signal generated every 6 days from our sequential algorithm might be expected to catch a large proportion of cargo or large passenger ship movements at a given seaport. As a specific example, ports along the coast of Libya have been subject to recent international attention, in part due to the refugee crisis in the Mediterranean and also because of the Libyan political instability. Some of them have been closed periodically due to international traffic. The port of Benghazi was closed in the first part of 2017, reopening on 5th October. This is verified in the change frequency plots below, which were generated directly from the interface. The change observations are partly confused by noise from open water, caused mostly by surface wave conditions, but the signals of interest are quite clear. So you can see the change map here, and in the left side is the port of Benghazi change frequency from 1st of January 2017 to 4th of October 2017, and the right is for 1st of January 2018 to 4th of October 2018. So you can see that there is an increase in the activity from 2017 to 2018. And then we have the proportion of change pixels in small area of interest around the main dock of Benghazi for 60 image time sequence. So this is the 60 image time sequence. There were about 900 pixels in all the AOI. Note the approximate alternation of arrivals and departures. So the arrivals are the positive definite changes. So the positive definite changes are these red lines you can see, and the departure are the negative definite changes, which are represented by the blue lines. Am I audible?
Yes, sir.
Yes, sir.
Yes.
Sir.
Now, second is the COVID-19 pandemic. So the COVID pandemic had a very significant effect on the Mediterranean tourist seaports. And unless you happen to be maybe a Venetian merchant or hotel operator, certainly a positive one, try using the same techniques as above on the main passenger dock in Venice, choosing a time series covering pre-COVID to the present. Another more future-oriented application of synthetic aperture radar change detection might be verification of the decommissioning of large open-face coal mines in the national programs for CO2 reduction. These are the programs for decommissioning of coal mines. So for the international community makes such policies so as to decommission these coal mines. And the Hambach open pit coal mine west of Cologne, Germany, is depicted in the single interval loner order change image below. The large digging and backfilling machines are visible in the chain series only by virtue of their movement. So cyan is the machine present, and machine to machine absent, and red is machine absent to machine present. So basically, red is machine absent to machine present, and cyan is machine present to machine absent. So the movement is happening from cyan to red. So you can see we can detect the movement from here, and would disappear if all mining activity were to stop. So this is single interval bitemporal changes from May 13 to May 19 over the Hembach open pit mine from a series of 55 images covering the year 2020. Then the third part is inundation. In part 3 of this series, we used a catastrophic flooding event in England to introduce and illustrate the sequential change detection algorithm. This is in fact a widely known application of synthetic aperture radar. Quoting from the Office of Outer Affairs, UN Spider Knowledge Portal, the usage of synthetic aperture radar satellite imagery for flood extent mapping constitutes a viable solution with fast image processing, providing near real-time flood information to relief agencies for supporting humanitarian action. The high data reliability as well as the absence of geographical constraints such as site accessibility emphasize the technology's potential in the field. And here, as another illustration, is an expert from Canty et al. 2020. Cyclone Idai, recorded as the worst weather event to ever occur in the southern hemisphere, made landfall near the city of Beira, Mozambique, on March 15, 2019, causing widespread inundation in Mozambique and Tanzania, and a death toll of more than 1,300. The figure 4 shows a sequence of 6 change maps generated with a Google Earth Engine time series of Sentinel-1A and Sentinel-1B images. The reduction of reflectance from water surfaces in both the VV and VH bands correspond to a negative definite covariance matrix difference, the rapidly receding of floodwaters to a positive definite change, which are the red pixels. So the red pixels are the receding waters. The green pixels are the waters which are coming in, like the flood is increasing. So this is the six. These are the 6 change maps of 15 in all for 16 images covering the period from January 1, 2019 through June 7, 2019. Each image has an area of approximately 3,000 kilometers square. The grayscale background is the temporal average of VB band of all 16 images. The maps read top to bottom, left to right, are for the intervals April 8, March to March 8, March 2 to 4, March 14 to 20. Okay. You can easily reproduce the above sequence with the interactive interface, remembering that negative definite changes are now shown as cyan. The change signal from within the partially inundated city of Beira, just to the east of the scene, is considerably less convincing, as you can also verify yourself. This is due to the predominance of so-called double bounce scattering from built-up areas, an effect which is present in both dry and flooded areas. Next example is vegetation. So when contrasted with visual or infrared remote sensing data, individual synthetic aperture radar images are of relatively limited use for detecting or classifying different vegetation types. Time series of radar images have some potential for supervised classification. See, for example, Canty 2021. If full polarimetric images are acquired by the satellite antenna, as is the example for the RadarSat-2 platform, then 3x3 quad-pole covariance matrix can be transformed in various ways to generate polarimetry indices for qualitative and quantitative physical information. And okay, so here we can see a change map, the CMAP band, showing the most recent significant changes in the time interval January to November 2018, generated from a series of 51 images over an agricultural region near Zulich, Germany. Right is the RGB composite of Sentinel-2 image acquired over the same area on July 2, 2018. Roughly 4 classes can be distinguished in the left-hand image. Black, which is no change. So these are the forests, motorways, built-up areas, villages. Light blue is the early harvesting winter wheat. Orange or green is the late summer harvesting, which is rapeseed. And red is the autumn harvesting, which is sugar, beet, corn, etc. This is partly guessing, but the dynamics could well be included as an additional feature in the supervised classification scheme. For instance, to complement the spectral bands of a cloud-free Sentinel-2 image, such as shown in the right-hand figure. An extremely topical theme associated with vegetation changes is, of course, deforestation, either intentional, that example conversion to non-forested land for agriculture use, or accidental, example bushfires. A drastic example of the latter was the fire that destroyed almost all of the forest of Kangaroo Island, Australia. So we can see from the Tour Kangaroo Island website, fire started on the north coast of Island on 20th December 2019 from lightning strikes, and by the 30th December were relatively under control, burning within contained lines. On the night of 30th December, more lightning strikes hit the island, this time within the Ravine de Casor Wilderness Protection Area, north of the Flinders Chase National Park. As conditions deteriorated, emergency service personnel worked closely with the community around the western end of the island. And by the 2nd January 2020, evacuations began. On the 3rd January 2020, the western end of the island, home to Flinders Chase National Park, and the adjoining Ravine de Casors Wilderness Protection Area, was burned along with Kelly Hill Conservation Park. Fires continued to burn across the island. For some weeks, and 2 lives were lost. Many businesses, homes, farms were lost. The images shown below, all of which were generated with the widget interface, confirm the above scenario and also indicate how well the Sentinel-1 time series analysis complements visual or infrared remote sensing data. So you can see the time series. Okay. So you can see that you can use this for even deforestation. So this is an example from deforestation. And this concludes the community tutorial series on synthetic aperture radar change detection. For readers that would like to delve more deeply in the theory, here are the relevant publications. Thank you for reading and happy Google Earth Engine. Okay. So now we will see this next tutorial, which is groundwater recharge estimation. Okay. So the implementation of the Thornwright-Mather procedure to map groundwater recharge. So groundwater recharge represents the amount of water coming from precipitation reaching the groundwater table. Its determination helps to better understand the available or renewable groundwater in watersheds and the shape of the groundwater flow systems. One of the simplest methods to estimate groundwater recharge is the Thornwright-Mather procedure. This procedure was developed by Thornwright and Mather. The idea of this procedure is to calculate the water balance in the root zone of the soil where water can be evaporated into the atmosphere under the effect of heat, transpired by vegetation stored in the soil, and eventually infiltrated when stored water capacity exceeds the field capacity. This procedure relies on several parameters and variables described as follows. So you need the information about the soil texture, that is whether the soil is sand and clay, has sand and clay content, to describe the hydraulic properties of the soil and its capacity to store or infiltrate. Second, you need the meteorological records, precipitation and potential evaporation, evapotranspiration. Of course, groundwater recharge can be influenced by many other factors such as slope of the terrain, the snow cover, the variability of the crop or land cover of the irrigation. In the following, these aspects are not taken into account. In the first part of the tutorial, the Earth Python API will be initialized, some useful libraries imported, and the location or period of the interest will be defined. In the second part, open land map datasets. So this is the open land map datasets. It's also called Open GeoHub. So you can see that these are the different open land map datasets on Google Earth Engine. And if you just go here, so these are from environmetrics. The long-term mode is land surface temperature, day and night time based temperatures, SD and differences, standard deviation and differences at 1 kilometer based on the 2000 to 2020 time series. Okay. So in the second part, open land map datasets related to soil properties will be explored. Wilting point and field capacity of the soil will be calculated by applying some mathematical expressions to multiple images. In the third part, evapotranspiration and precipitation datasets will be imported. A function will be defined to resample the time resolution of an EE.image collection and to homogenize time index of both datasets. So both datasets will then be combined into one. In the fourth and final part of the TM procedure, will be implemented by iterating over the meteorological EE.image collection. Finally, a comparison between groundwater recharge in two places will be described and the resulting mean annual groundwater recharge will be displayed over fronts. So we will first initialize the Earth Engine API. We have successfully saved the authorization token. We'll import the different libraries. Here you see we also use this Branca library. So this is for the custom color maps. We'll see how to use them with Folium. So some input parameters. We additionally define some parameters used to evaluate the results of our implementation, particularly the period of interest to get meteorological records, a location of interest based on the longitude and latitude coordinates. In the following, the point of interest is located in a productive agricultural region, which is about 30 kilometers outside the city of Lyon, France. This point is used to evaluate and illustrate the progress of the described procedure. So we have this point. We create an E geometry point, lon, lat. Scale is 1000 meters. Okay. So from soil texture to hydraulic properties. So two hydraulic properties of the soil are commonly used in the TM procedure. So one is wilting point, which represents the point below what water cannot be extracted by plant roots. And then we have the field capacity, which represents the point after which water cannot be stored by soil anymore. After that point, gravitational forces become too high and water starts to infiltrate the lower levels. Some equations given by Saxton and Rawls are used to link both parameters to the texture of soil. The calculation of water content at wilting point can be done as follows. So you can see that the amount of so the water content at wilting point is equal to the water content at 1500 T plus 0.14 theta 1500 T minus 0.002. And what is theta 1500 T? It is minus 0.024 S plus. So it's a function of S and C and OM. Now S is S represents the sand content of the soil in mass percentage. C represents the clay content of the soil in mass percentage. And OM represents the organic matter of the soil in mass percentage. Similarly, the calculation of water content at field capacity can be done as theta Fc equal to theta 33t. So it's a function of theta 33t, and theta 33t in turn is a function of S, C, and OM, which is sand, clay, and organic matter. Now, determination of soil texture and properties. So in the following open land map datasets are used to describe clay, sand, and organic carbon content of the soil. A global dataset of soil water content at the field capacity with a resolution of 250 meters has been made available by Hengel and Gupta. However, up to now, there is no dataset dedicated to the water content of soil at the wilting point. Consequently, in the following, both parameters will be determined considering the previous equations and using the global datasets giving the giving the sand, clay, and organic matter contents of the soil. According to the description, so this description you can go back and see for the open land map data. These datasets are based on machine learning predictions from global compilation of soil profiles and samples. Processing steps are described in detail. Information is given at 6 standard depths, so 0, 10, 30, 60, 100, and 200 centimeter, and 250 meter spatial, the horizontal spatial resolution. The standard depths and associated bands are defined as below. So these are the standard OLM depths, and the bands are defined here. So this is B plus string SD for SD in OLM depth. So this will be B0, B10, B30, B60, B100, and B200. Now we define the function to get the E dot image associated with the parameter we are interested in. Example, sand, clay, organic matter, organic carbon content. So we define this function get soil prop param. If param equal to sand, you select this snippet, open land map, SOL. So from here we get the snippet. Here we get the scale factor. And then we return, so else if the parameter is not in sand, clay, and or C, you return an error. Otherwise, you return this datasets, which is e.image snippet, okay, and multiply with scale factor. So this is the scale factor to get the data in kg per kg or percentage. We apply this function to import soil properties. So we get the sand, clay, and organic carbon or organic matter. To illustrate the result, we define a new method for handling earth engine tiles and use it to display the clay content of the soil at a given reference depth to a leaflet map. So we define this add E layer function. Now we add to the folium.map, we add this E layer. So add the earth engine drawing method to folium, and my map equal to folium.map, location equal to latlon, zoom start equal to 3, and you set the visualization parameters in a dictionary. My map.add E layer, you display sand and add a marker at the location of interest. Add a layer control panel to the map and display the map. So you can see that we have a marker here, and we have displayed this map, which is the sand percentage in kg per kg, or the sand percentage. I think either it should be in kg per kg, or yeah, it's in percentage. Yeah. Now a function is defined to get the soil properties at a given location. The following function returns a dictionary indicating the value of the parameter of interest. For each standard depth, the function uses the e.image.sample method to evaluate the e.image properties on the region of interest. The result is then transferred client side using e.image.getInfo method. In the example below, we are asking for the sand content. So you can see that we create this function local profile, which takes in as input the data set, the point of interest, and the buffer. So we will sample this data set first over this point of interest and with the buffer. The buffer is basically nothing but basically the scale which we have as 1000 meters here. Dot select OLM bands. So we select the OLM bands here. Dot get info. So this gives us the properties at the location of interest and transfer to client side. Selection of the features or properties of interest and reshaping of the dictionary. So we reshape the profile which has the keys as so key and the value is round number of val comma 3 for key comma val in profile dot items. So key and value are coming from this profile, and it is coming as so you are rounding off the value up to the decimal 3 and you are having this key. So we will see what is the sand content profile at the location of interest. So sand content profile at the location of interest B0, which is at 0 centimeter, is 0.36, which is 36%. 10 centimeter, 100 centimeter, 200 centimeter. Okay, and this is B30, B60. Clay and organic content profile. So similar to the sand, we can get the clay and organic content profile, and then you can do data visualization in the form of a bar plot. So define definition of the label locations, definition of the bar width. So let us see this. So we can see that we have the majority as sand, then we have clay, and then we have the organic matter. Expression to calculate hydraulic properties. Now that soil properties are described, the water content at field capacity and the wilting point can be calculated according to the equation at the beginning of this section. Please note that in the equation of Saxton and Rawls, the wilting point and field capacity are calculated using the organic matter content and not the organic carbon content. So in the following, we convert the organic carbon content to organic matter using the corrective factor known as the Van Bemmelen factor. So you can see that organic matter can be converted to organic carbon content can be converted to the organic matter content. And several operators available are available to perform the basic mathematical operations on image bands: add, subtract, multiply, divide. We already seen that, and we will use this multiply operator. So, and then from that we will extract the organic matter content profile. So the organic matter content profile at the different location at the location of interest, they are basically 4.3%, 4.3%. This is 0.9%. This is 0.9%. When the mathematical operator to apply to the E dot image becomes too complex, the E dot image dot expression is a good alternative. We use it in the following code block since the calculation of wilting point and field capacity relies on multiple parameters and method images. This method takes two arguments. So the first is a string formalizing the arithmetic expression we want to evaluate. And the second is a dict associating images to each parameter of the arithmetic expression. So we can see the wilting point and the field capacity. We can initialize them with 0. We can create it as an image. And then we can say for key in OLM band. So these are basically B0, B1, B2 up to not B0, B1, B at 0 centimeter at 30, 60. So we can get the clay, sand, and organic matter at appropriate depth. Now we can calculate the wilting point, so which is theta 1500 Ti equal to E dot image 0 dot expression. So this is the expression that we use, and we give the in the dictionary we give what are the variables to use, and we rename this to T 1500 Ti. And the final expression for the wilting point we use as this one, and we rename it to wilting point WPI. And so wilting point equal to wilting point dot add bands WPI dot rename key. So as add as a new band of the global wilting point image, global wilting point E dot image, and do not forget to cast the type with the float. Same process for the calculation of field capacity. The parameter theta 33t is needed for the given depth. So this here you are calculating theta 33t, and the final expression for the field capacity of the soil. Okay, and the field capacity you rename it as to Q. So this was the okay. So here we basically computed the wilting point, the field capacity, and we can print what is the local profile at different depths. So the wilting point here is 0.152, 0.158, 0.175. The result displayed using bar plots is as below. So this is water content at wilting point 15.2%, 27.1%. So these are the hydraulic properties of soil at different depths. Now we have to get the meteorological data sets. So how we will get these meteorological data sets? So the data set exploration. So the CHIRPS data will be used. So climate hazards group infrared precipitation, and MODIS TerraNet, it gives the evapotranspiration on 8-day basis. Both the data sets are imported as follows, specifying the bands of interest using select and a period of interest using filter date. So you can see that from CHIRPS image collection, we select precipitation and filter date. And from MODIS, we select the potential evapotranspiration, and we also select the quality control flag PT underscore QC, and we filter for the I date to F date. Now we can have a closer look at around our location of interest to evaluate the property of an E.image collection. The E.image collection region method is used and combined with E.image collection get info method for client side visualization. So you can see that you have this PR. So you can just say PR.getRegion, and this is the point of interest, and you give a scale.getInfo. So this will give you the values in NumPy or in the list, and you just say pprint.pprint local PR:5. So 0, 1, 2, 3, 4, 5. You have the ID, longitude, latitude, you have the time, and you have the precipitation. So 5 variables of precipitation is 0 in all. We now establish a procedure to get meteorological data around a given location in the form of pandas data frame. We've seen this yesterday. Okay. And we do the same for potential evaporation. Looking at both the pandas data frame, so you can see here shows the following points. The time resolution between both the data sets is not same. For some reasons, the potential evapotranspiration cannot be calculated at some dates. It corresponds to lines where the quality indicator ET underscore QC is higher than 1. Both issues must be handled before implementing the iterative process. We want to work on a similar timeline with potential evapotranspiration and precipitation, and we want to avoid missing values. Retrace the time resolution of an A.image collection. So to address these issues, we make a resampling of both datasets by month. So when potential evapotranspiration cannot be calculated, the monthly average value is considered. The key steps and functions used to resample are described below. So the first is a new date index is defined as a sequence using E.list.sequence method. Then a function representing the resampling operation is defined. Function consists of grouping images of the desired time interval and calculating the sum. Sum is calculated by taking the mean between available images and multiplying it by the duration of the interval. The user supplied function is then mapped over the new time index using .map. So you can see here this one, some resampler function. Okay. So you we basically have now have the potential precipitation. We have the evapotranspiration. and we have the soil properties. So we evaluate our the result on our location of interest. So we have, so you can see the blue one is the precipitation, the yellow is the potential evapotranspiration, and we now use the TM procedure to basically compute the groundwater recharge. So yeah, I will not go into details of this algorithm. So this is the recharge calculator. The TM procedure can now be applied to meteorological e.image collection. Let's have a look at the result below, around the location of interest. Okay. So here you can see precipitation, potential evapotranspiration, APWL, ST. So these are the other terms, and then we have the recharge. Okay. The result can be displayed in the form of a bar plot. Okay, so you can see that how much of groundwater recharge is happening. So the result shows the distribution of precipitation, potential evapotranspiration, and groundwater recharge along the year. It shows that in our area of interest, groundwater recharge generally occurs from October to March, even though a significant amount of precipitation occurs from April to September. Evapotranspiration largely dominates because of high temperatures and sun exposure during these months. The result is that no percolation into aquifers occurs during this period. Now, the annual average recharge over the period of interest can be calculated. To do that, we sample the data frame that we just computed. This one, okay, so then you can just plot this thing on the map, and these are the papers. So, yeah, okay, anyways, yeah, so we finished these main community tutorials of Google Earth in